Hello everyone and welcome to another physics lesson. Today's video is going to be about periodic motion, and after watching this video you should be able to describe what periodic motion looks like, and we're going to actually look at pendulum motion and understand some of the properties associated with it and work a problem or two dealing with pendulums. So let's get right into it. So the first thing I want to talk about is the vibrations created by waves, right? And basically there's 4 steps to creating a vibration. First, there's a disturbance caused by a force, right? And so I guess let's kind of just talk about like a mass hanging from a string, kind of like a pendulum, right? Which where we're going with this. Basically, if you push this mass to the left, that's a disturbance by a force. Okay, it was just hanging there fine and dandy, and now it's been moved, and that's a disturbance. And basically, that, as we probably know on Earth, what ends up happening is if that pendulum is hanging from, say, the ceiling or whatever, it's going to be brought back to its original position, which is called the restoring force, and I'll abbreviate that with RF. The restoring force brings it back to its original position. The thing is now, this pendulum has inertia, and it's going to actually move past this center point and keep on going. So it's going to end up over here. And then eventually friction and air resistance slows it down, which is called dampening. And it stops and then swings back the other way. Okay? And this we're going to learn is something called simple harmonic motion. And basically waves are very similar to that. We're going to see a lot of similarities. So except where we're going with this is we're going to start to talk about waves. But before we do that, we talk about some other maybe easier things to visualize in terms of simple harmonic motion, and pendulums and springs are some of those types of things. Okay, so my examples down here of this type of stuff that happens would be like a guitar string. If you pluck a guitar string, it vibrates back and forth very rapidly, but it does do that. Or say a bobblehead. If you poke the bobblehead, it swings to one side, then it swings back the other way and keeps going back and forth, back and forth. Or if you hit a tuning fork, that tuning fork is actually vibrating from side to side. All right, and basically it's going through these 4 steps, okay, for a vibration to occur. If we take a look at that as like a graph, you will notice a distinct pattern here. Basically what's going on, and I need to quickly change my pen color so you guys can actually see what I'm writing. What's going on is, let's say I have a motion sensor. Okay? I have a motion sensor, and I have it like right here. Here's this motion sensor, and I have, I'm not a good drawer, but pretend that's a spring, and there's a mass hanging from the spring. Okay, and there's my motion sensor, and it detects the motion, and it detects how far away the mass is, and it's found that it's I'm here at this position. It's 0.6 meters away from this motion sensor. Okay, now let's say at like a second or two later, I take this spring and I pull the mass down to here. So it's like right above the motion sensor. And so the position of the mass relative to the motion sensor is pretty close, right? It's at 0.2 meters away compared to before it was at 0.6. So I've changed the distance of that mass. And let's say now I let it go. What's going to happen? Well, I think we all know that the mass is going to rise upward, right? And so if I have my motion sensor here, my mass would be maybe at this point. As time progresses, it would bounce up to here, and then eventually it might be like up here. And then we know that we want it to get back to even or normal, and so maybe now my mass is swinging back down to here, and then it's going back down here, and you kind of notice it's going up and down, okay? And that's called simple harmonic motion. That's what this graph is basically showing, is if I had a motion sensor at all of these points, and I was graphing the motion of this mass going up and down on the spring, this is what it would look like. Okay, this is what it would appear to look like. Now, realize I can't draw this all right on top of each other. It's not that I'm actually swinging this mass from side to side. So I just have this as like freeze frame shots over time. Okay, so the mass is just bouncing up and down, up and down. It's not swinging side to side. Okay, so we're going to take a look at some vocab terms here. We have two terms that can get kind of confusing at times. The first is called the period, and the period is basically just the length of time it takes for an object to complete one full cycle of its motion. So if we go back to like this idea of a pendulum, if I have a pendulum here and it takes 2 seconds for it to swing all the way here and then swing all the way back, that would be its period. Okay, it would take two seconds for it to complete one full cycle. And I have an example here of a pendulum will sometimes take 2 seconds for a period, and then a piano string has a very rapid period where it's 0.0038 seconds. So I mean that happens very quickly. The period is related to the frequency, and the frequency is basically the number of cycles occurring usually per second. All right? And frequency can be found, which a lot of times it looks like this. Frequency equals 1 over t, 1 over the period. Because what you're doing is you're actually finding out how many cycles happen per second. So if I go up to my example here again with this pendulum of a period of 2 seconds, I can take 1 divided by 2, which equals 1/2, right? And so what it's saying is there's a frequency of a half, so it can complete half of a cycle in 1 second. It'll swing to here, and then that's it. That's one frequency, or that's the frequency of it. It can make one swing, half a swing, I should say, per second. It can't complete the full swing. Okay. These two terms get kind of confusing, but we'll practice them a lot in class. But again, period, how long it takes to complete one full cycle, and the frequency is how many cycles can be completed per second. And sometimes it's a half or a fourth or an eighth or whatever the case may be. Okay? Because if the period's longer than 1 second, it's going to be the frequency is going to be a decimal. Okay. What is a pendulum anyway? A pendulum basically consists of, I say massive object, but I don't want you to think like it's like a truck hanging from a wire or something. Basically, there's an object hung by a string from a fixed support. And that massive object, and the reason why I'm saying massive is because it is relatively large compared to the string that's holding it. The mass of the string is we usually consider as irrelevant compared to the mass of what's called the bob. So basically, if I draw the ceiling here and I put a bob on a string, the mass of this is substantially more than say the mass of this little string here, and so that's what we really care about, is the mass of that bob. So when a pendulum is displaced from its equilibrium position, which is what this is called, where it's just hanging there doing nothing, it swings in periodic motion. And so let's take a little look at pendulum motion and the forces acting on it. Here we've got this pendulum swinging right here in this middle picture is equilibrium. Okay, it's not doing anything, and you'll notice the tensional force of the string is equal to the force of gravity. There's no net force, it's just sitting there. But if I give it a push or a pull in a direction and pull it and swing it from equilibrium, remember there's this thing called the restoring force that's going to cause it to swing back that way, because gravity is always going to just pull downward, and if you break gravity into its components, you're going to have a piece that points in this direction and causes it to accelerate to the right. All right, so the force of gravity never does change in terms of its direction, but when you start to move this thing, now you don't have perfect straight down gravity and equal with the tensional force, so you have a component here pulling it to the right and causing it to swing, and then swing this way, and then it'll swing back that way, and so forth. Okay, so kind of cool things that should be pointed out with a pendulum, and let me just quickly change my pen color here. If we draw the ceiling, so let's just draw a nice ceiling there, and I'm just going to draw a pendulum in 3 points of its swing. Okay, I got one here, one there, and 1 there. Okay, so you have to imagine that this guy is swinging, you know, back and forth. Okay, there's some things that you can kind of use to help you in terms of solving pendulum problems. At this point here, where it's at its highest point in the swing, its potential energy is at its max. Okay, remember, potential energy is related to its height and gravity, and basically when it's at its highest point in the swing, its potential energy is at its max. Now when the potential energy is at its max, its kinetic energy is 0. Okay, it has no kinetic energy at this point because it's got a maximum amount of potential energy. The velocity at this point is also 0. Okay, and the reason why is it has no kinetic energy. Kinetic energy is the energy of motion or movement, and it has none. It stops for just a second, it's paused, and it has a maximum amount of potential energy, and it has no kinetic energy or velocity. At this middle point, the potential energy is actually 0. It has none, but all the potential energy has been transferred into kinetic energy. And so in the middle of the swing, that's when you have a maximum amount of kinetic energy, and its velocity is at a max also. All right, and then on the other side, we would actually just repeat what we wrote over here. The potential energy is again at a max, the kinetic energy is 0, and the velocity is also 0. And so this really shows the conservation of energy really well, actually, because as it swings, it's gaining potential energy as it goes up, gaining potential energy, it's losing kinetic energy, the velocity is slowing down, and then once it hits that point, it stops, and then it starts to swing back down this way. It's then, as it's swinging down, it's losing potential energy but gaining kinetic, and then as it starts to swing up, it loses kinetic but gains potential. And so spend some time kind of thinking about that, looking at that picture, and I think it'll make sense to you if you do that, because it'll make the problems a lot easier to solve. So just some information on pendulums, and this is kind of some important stuff here. The period of a pendulum, or the time it takes to complete one full swing or one full cycle, is based only on actually 2 things, believe it or not. The length of the string and the acceleration due to gravity, which that kind of makes sense. I mean, if you put a pendulum up on the moon, it's probably going to swing slower than, say, on the Earth. And the length of the string is also going to dictate how long it takes for a period to complete. Now, one thing that students frequently get confused, and this is really an important component here, the period of a pendulum is not dependent upon the mass of the bob, which seems crazy, you know, that you could have a 5-pound bob, you could have a 10-pound bob, a 30-pound bob, but none of that matters in terms of how long it takes for it to swing back and forth. It's only dependent on the length of the string and the acceleration due to gravity. So that's an important piece. I would definitely have that written down, that it is not dependent upon the mass of the bob. Now you may be asking yourself, well, what is the formula for a pendulum? Let me get something that you guys can actually see here. The formula is typically written as TP, so period of the pendulum, equals 2 pi square root length of the string divided by gravity. Okay? And you'll notice mass isn't in this formula whatsoever, and that's because it doesn't matter. The mass is not important. So again, the period of the pendulum is equals 2 pi times the square root of length times the gravitational constant. So if you're on the moon, g's going to be different than, say, on the Earth. All right. So this will be a kind of important formula, and we're going to use it in the next problem right now. So it says, let me just get my pen colors here, something different. We'll go with red. A grandfather clock is designed such that each swing, or half period, so just a swing going from either left to right or right to left, of the pendulum takes 1 second. How long is the pendulum in the grandfather clock? Okay, so how long is the string in the grandfather clock? Okay, so we got one piece of information for sure. The period, it says 1/2 period is 1 second. So what's 1 period? 1 period would be 2 seconds. Okay. The other thing we also know is it doesn't say we're on like some weird planet, so our g is 9.8 meters per second squared. And basically to find out the length of the string, we're going to use the formula that we just talked about, 2 pi square root L over G. Okay, and so what are we trying to find out? Well, we're trying to find out L, so we want to get L by itself, okay, and we know this other stuff. And so to get L by itself, basically what we got going on here is I'm going to square, I'm going to square everything and get rid of this square root. And so I have TP squared equals 4 pi squared, and then we have L over G. And then basically what this works out to being is that if we get rid of it or do our multiple or our algebra, we have L equals TP squared times G over 4 pi squared, and that will give you L. So our T is 2, our G is 9.8, so I guess I can write this here out here. We have 2, I'm not going to put units just because I'm running out of space here, times 9.8 divided by 4 pi squared. And if you do that math, you'll get an answer of about 1 meter rounded. Right? So what we found out is that the length, this L, is about 1 meter for this grandfather clock, for the pendulum, I should say. Okay, that takes care of this video. We will see you guys next time.